I have a couple number theory problems for you this month. We're going to start by finding the least positive base 10 integer that can be written as a 4-digit number in base 3 and a 3-digit number in base 4. The first thing I'm going to do is I'm going to underline that least so I remember what I'm looking for here. And then, let's see. You know, I'm facing a number-based problem. I like to think about the number base I understand best. That's right, base 10. So I'm going to think about 4-digit numbers in base 10. Now in base 10, those 4-digit numbers, they go from 1,000 all the way out to 9,999. That gives me a guide for how to write down that range for base 3. For the smallest one, I take the smallest possible digit I can put in each place. Up front, I have to put a 1 in. I can't put a 0 in, but all the rest I can drop zeros in there. Looks a lot like the smallest base 10. But the largest is going to be different because there are no 9s in base 3. All I get in base 3 are 0s, 1s, and 2s. So I have to put the largest digit I can in each place. I'm going to put 2, 2, 2, 2, base 3. Now, of course, I need to think about these in base 10 because my answer needs to be base 10. So what's this in base 10? Well, once again, I'm going to look at base 10 to figure out how to do that. Up here in base 10 land, I got 1s. I have 10s there. I have hundreds, those are 10 squared, and I have thousands, those are 10 cubed. Same game down here, but with 3s instead of 10s. I have 1s, I have 3s, I have 3 squareds, those are 9s, and 3 cubes. If 1 3 cubed, that's 27. I could do kind of the same thing over here. I got 2 1s, 2 3s, 2 9s, 2 27s. But instead of doing that, I'm going to be a little lazy. I'm going to think about what's one higher than this. Well, then I'm going to have the smallest 5-digit number in base 3, which is 1, 0, 0, 0, 0. That's the next power of 3 up from 27. That's 81. This is 1 less than 81. That means this is 80. And this gives me a great guide for what to do to figure out our base 4 numbers. Now we only have 3 digits, so the smallest one is 100, base 4. But I get an extra number that I can use as the digit. I get to use 3s now, so my largest 3-digit number is 333, base 4. Same drill to convert these into base 10. We got 1s, 4s, 4 squared is 16. Then over here, this is 1 less than 1, 0, 0, 0. Base 4, that's 4 cubed, that's 64. This is 1 less than 64, so it's 63. And I look back at my question, figure out what it is we're supposed to find, the least positive base 10 integer that fits in both of these ranges. We see it sitting right there. It's 27. And we're ready for the next problem. Oh boy. All right, in this problem, Q is the product of a prime number and a perfect square. It's also the product of a different prime number and a perfect cube. And we're looking for the least possible value of Q that fits this. Once again, I'm going to underline that least so I remember what I'm looking for here. I got to turn these words into equations. Maybe we'll be able to do something clever with them. So first, Q is the product of a prime number. Let's say P is a prime and a perfect square. So P times M squared. And we're also told it's the product of a different prime number. Well, I can't use Q for that different prime number because I'm already using Q. I'm going to use R. And then times a perfect cube. 5 variables, 2 equations. This is not looking so good. All right, I have a problem here about multiplying integers. When I have a problem about multiplying integers, I like to think about prime factorization because those primes are kind of the building blocks of our integers. So I'm going to think about the prime factorization of Q. I know a little bit about that prime factorization. I know it has a P in it because Q is P times something. So I know I have a P in it. I just don't know what power I'm raising that P to. I also know this prime factorization has an R in it. I just don't know what power I'm raising the R to either. Let's see. Well, I do know up here. I look at this and I see, well, if there's a P and an R in the prime factorization of Q, well, there's no R's in the P. There has to be an R in the M. Right? You know, m's prime factorization has to include an r so we can get something in q, get some r's in q. But then I'm going to square it. So all the r's that are in m's prime factorization, they're going to get squared and make a bunch of r squareds. That means the exponent here for q, the exponent of r, it's got to be even. That's interesting. Then I look down here and I realize, well, wait a second. Not only does it have to be even, it has to be one more than a multiple of 3, because if there are r's in n's prime factorization, well, they're going to get cubed, so I'm going to have a bunch of r cubes, but then I'm going to have one extra. So this power here, it's even, and it's one more than a multiple of 3. Now, I want the least possible q, so I want to pick the smallest number I can that is even and one more than a multiple of 3. It has to be positive as well, so I'm going to pick 4. That's as good as I can do. It's as small as I can make it. We're going to do the same game over here for p. I look at the second equation here and I see right away I need a p in n's prime factorization because I know q has a p from up here. But then any p's that are in n's prime factorization, they're getting cubed. So in the end, I'm going to have some p cubes up here, put them all together. This exponent has to be a multiple of 3. And then I look up here and I see that this exponent also has to be one more than a multiple of 2. So it has to be odd. This has to be odd, has to be a multiple of 3. The smallest I can get it is 3. And there's my prime factorization of q. I don't want to stick in any more primes because, again, I'm looking for the least possible value of q. And then I think about what primes I actually want to stick in here. Of course, I'm putting in 2's and 3's. And I'm going to put in the 2 with the higher exponent. So the smallest I can make q is 3 cubed times 2 to the 4th. Now I'm going to pair off 3 of these 2's and 3's. I'm going to write this as 6 cubed times 2. Because 6 cubed, that's 216. 216 times 2 is 432.